ahead and get started though. Welcome to lecture 17. Today we'll be talking about minimum spanning trees. Before we start, let's go ahead and talk about some announcements. So first things first, welcome back. I hope your spring break was good. I hope you had some time to rest and recover from the semester, and that, for some of you, catch up on all the work that that you had to do. For me, it was a mix of relaxation and catching up. Um, we have some announcements that we want to cover, so let's go ahead and go over them today. Uh, we want to know, first off, homework 3 corrections is due on Thursday at 11:59. I created a small video in case you're not sure how to do homework corrections. It's like a 2-minute video. Check them out, and you should be able to use this for all homework corrections going forward. There's a quiz as usual next Thursday. It's going to be on distros, which we covered before the spring break, and then MSTs, prims, and cruscals, which we covered, which we're covering right now. Homework 7 will be released by this Thursday. If you need me for anything, I don't have access to my GSU email right now. It's really important that you send me a Piazza post instead, make a private Piazza post. And it's going to take me a week to get my email back. So for now, just make a private Piazza post in case you need me. You can see that some people have already been doing that. Let me hide those though. So keep that in mind. Other things you should know, which I think a lot of people will like. The final will not be cumulative. So I looked at our topics for the rest of the semester and I realized they're all kind of hard, right? They're all more challenging topics. We're going to cover material that is fundamentally going to make you think really hard and like practice really hard in order to master them. And I want to focus in on them for the final. So instead of trying to cover everything from the beginning of the semester all the way toward the end for the final, we're only going to cover the last third of the class. And to compensate for that, or to adjust for that, we're actually going to have 2 take-home assignments where you'll be able to work in groups to kind of complete them. You'll be able to ask questions on Piazza, which will serve as both review for exam 1 and exam 2 and also corrections. So I'll release these sometime in April, which will give you a chance to basically earn points back on your exam, but also double as a way to review what you learned, in the first third of the class where we talked about sorting and runtime and recursion, and then the second half, which was all about trees and graphs and binary search trees and all of that. And lastly, we'll end, and on the final, we'll actually cover this new material here. All right. Hopefully this helps relieve some stress. I know some people were feeling a little bit stressed about the fact that the final is going to be this big scary thing. I'm trying to make it a little bit less scary. I'm going to try to make it so that you have some opportunities to catch up and also focus in on this material, right? Like I just alluded to, though, we're about to tackle more challenging topics in this course, including more advanced graph algorithms, programming techniques, theoretical concepts. This isn't really targeted toward you. This is targeted to the people watching this video. Hi, people watching this video, please come to lecture. Please come to lecture and participate, because that's the best way for you to keep up with the material and for you to remember the stuff that we go over, right? In lecture, we actually go over material that is trying to help you think and retain the information that we cover. If you just try to watch all the videos at the last minute before the exam, you're not going to do well in this class. Like fundamentally, this is not one of those classes where you can watch me on 2 times speed and watch all like 24 videos all at once, right? That's not going to help you. What you need is day in, day out, week in, week out to kind of sit with the material, work through the homeworks, work through the quizzes, make sure you understand the definitions, make sure you review everything. And that happens week over week, right? If you are not able to regularly attend class due to any of these circumstances, please let me know, make a private Piazza post, and we'll work out an alternative solution for you. All right. So those were the announcements. Let's go ahead and talk about what we want to talk about today. There's a question in chat. What are the stats for lecture attendance? I'm computing those stats in the background. If you've been showing up to lecture and participating every single lecture, even if you've missed 1 or 2 lectures, you've probably gotten full points for lecture participation. All right. Remember, in order to get full credit, you are measured on not only how much you participate, but how you put effort into the class, as well as how you help other people. So there's going to be people who probably get closer to like a 3 or 4 out of 5% of your total grade. And then there's going to be people who maxed out 5 out of 5 because they were doing awesome. And then there are people who go above and beyond who will get extra credit based on the work that they've done or the ways they've contributed to the course. Let's talk today about minimum spanning trees. Today, we're going to review a concept that we're going to talk about that's related to graphs. Minimum spanning trees are things we find in graphs. We're going to be talking about graphs for the rest of the semester. So hopefully you now feel much more comfortable with graphs now that you've had an exam on it and that you've studied it and you've sat with it for a little bit while longer. But graphs aren't going to go away. So please let me know if you have any questions or concerns. We'll go over the motivation, the definition, some examples, and then we'll look at two algorithms on how to actually find minimum spanning trees. One is called prims, one is called Kruskal's, and we'll go over the intuition, the pseudocode, and some examples and some analysis for both of them. All right. Give me a MST in chat if you're ready to go. We're ready to start. Let's just make sure that everyone can hear me and you're ready to go. Nice. Okay, so let's go ahead and look at a motivation. We're just going to take some time to stare at this graph, right? I want you to take 30 seconds and tell me everything you know about this graph. Like, tell me the graph properties, right? So this isn't meant to be like a pop quiz or anything. It's just a way for you after spring break to start thinking about graphs again. So graph properties. What are the graph properties? Here, right? What are the properties of this graph below? And just to get everyone feeling like they remember graphs and remember what we covered before spring breaks, go ahead and type in now. What do you think? All right, people are saying that there are, in this case, six vertices / nodes, right? People are saying that this is undirected, right? There are no arrows in between the nodes when you have edges, right? This goes one way and the other for each edge. And in this case, it is weighted. There are nodes, there are edges that have weights on all of the, there are weights on all of the edges. And it is also cyclic, right? You can see that you can go from C to B to D to C again. And that's a loop. You could go C to D to F to C. So this is definitely a graph with cycles. Other things we care about, there are letters for labels. Not that that matters too much, but for completeness, we'll include all of that in. Okay, cool. So imagine for a second that you're Comcast, so you're an internet provider, and you want to wire up the entire state of Georgia with internet service such that each city is connected to every other city. You don't actually care if each city is connected in a way that's efficient. You only care if the cable cost, the cost to go from city B to city C, for example, is minimized such that the total amount of cable you have to use, and these edges representing cables and these nodes representing cities, is minimized as much as possible. So what I mean by that is, for example, you can see all of these different edges. We're going to pretend like they are wires you can run between these nodes, which are cities. And each number on the edge represents the cost it takes to run wire between cities. So for example, if we want to run wire between D and F, it would cost us 6, right? And we want to minimize the amount of cable used because we're Comcast and we're cheap. You can see that I don't like Comcast very much, but I don't think most people do. All right, I'll give you about 20 seconds to think about this, and then we'll look at it together. What I want is a set of edges that will be required in order to wire up all the cities. All right. That minimizes the total edge cost. So for example, we probably want in our set like A to C, because that looks really cheap, right? Going from A to C is really, really inexpensive here. It only costs us 1. So maybe we want to include that, but we want to include other things too. I'll give you another 10 seconds to think about it. All right, go ahead and type in chat if you have some answer, even if it's not complete, punch in what you have. If you are still confused and you're not sure what's going on, go ahead and put in a question mark as always. Remember, we don't necessarily want a algorithm to solve this. We just want a way to list out all of the edges we care about. Okay, we're getting some question marks. We're getting some edges. It doesn't seem like a lot of people have a complete picture yet, and that's okay. So let's go ahead and try to take a look together then. If we go from A to C, do we want to use this edge or not? Yes or no? Go ahead and type in chat. Why do you think we should use this edge? Yeah, we definitely should, right? Because it's really cheap, so that seems really good. Likewise, if you know we have to use that edge, how about C to D? Do we want to use this edge? right? Because C to D is really cheap too. And we want to connect A to C and also A to D. And you can go from A to D through C, right? So we want both of these edges. That's definitely something we want. And that's like good. That gives us some progress, right? We haven't reached B yet. We haven't reached F yet. We haven't reached E yet. So we're going to have to think carefully about that. Let's just think for a second. If we want to connect and go to E, do you think we have to use this edge? Yes or no? Right? We have to. There's no other way to get to E. There's only one option, like someone in chat typed. So we have to. Yeah, that's very good. Okay, now we have some options though if we want to connect the left side of the graph with the right side. So if we look at all the nodes here, excuse me, we have A, C, D, which are all connected, which is nice. And we want to connect it with F and E. We have two options here. We have CF and DF. Those are the only two options we really have to kind of join those parts of the graph together. I'll give you 10 seconds. Which edge do we want to pick? We don't want to pick both, right? Because we only need to connect A with F in one way. A lot of people are saying CF, right? Because that would give us the least amount of wire that we have to use. We use 4 here instead of 6, right? So we can get from A to C to F, and we can go to A to C to E. Now we can go to D to C to F. We don't really care about the number of hops or the cost. We just make sure that they're all connected, right? We literally do not care about the cost between individual paths. We just make sure that it's connected and that the number of that we have for the total cost, the total number of edge costs all added together is minimized. Now, lastly, we have to reach B. We have 3 options. We have A, B, C, B, and DB. Go ahead and type in chat which one you think we should use. Okay, some people are voting BC. Some people are voting AB. Any love from BD? No one likes BD, it looks like. And we have some question marks. All right, someone finally typed into chat. It doesn't matter. So what I'm asking is we want to get to B, right? B is the only thing that we haven't connected with the rest of the graph. So we have to pick an edge that goes from any of our existing nodes to B. All right, give me a B in chat if you understand that's what we're trying to do right now. Just making sure that we break it down for everyone because I saw a few question marks in here. Okay, well, we have 3 options. We can go through this edge, we could go through this edge, and we could go through this edge. Now, in this case, does it matter which edge we pick in this case? Yes or no? It really doesn't matter if we're trying to go and just minimize the amount of cable we're using, right? Some people would argue, okay, well, C looks like a central hub, so maybe we'll do CB. But remember, in our original problem, there was no indication that we wanted to like have a central hub or do any sort of efficient routing. We literally just want to minimize the amount of cost being used here. So for example, if we did AB, that would still be fine because B can reach any of the other nodes. Or if we want to do BD, that's totally fine because again, B can reach any of the other nodes. So we just care about the amount of costs being used for all of these edges, and we want to minimize that. We don't really care about the cost of the paths. So just to finalize, let's say we did AC here. We know we have to do CD. We know we have to do CF. We know we have to do FE. And we also, in this case, did BD, right? And the total cost here, if we add this all up together, the total cost should be 1 plus 2 plus 4 plus 4 plus 5, which gives us 16, right? At this point, I've done this lecture 2 different times, so I finally memorized all the numbers for figuring out the cost weights. Someone asked, well, if we went BC, wouldn't that minimize the cost of going to B to F as well as B to E? It would, but again, we don't care. Fundamentally, we do not care about the individual pairwise costs to go from any node to any other node. We only care about minimizing the total cost of this red lines. If all the red lines, if we add them all together, are cheap, then that's what Comcast cares about, which is why Comcast is not the best internet service. I'm just kidding. I have no idea how Comcast does routing. But we don't care about the fact that it takes longer to get from B to D all the way up to E if we went this way versus going through C instead. Okay. Good questions. Let's talk about the formal definition of what we just did. So we just went over an example of a minimum spanning tree. A minimum spanning tree is a tree with a connected graph such that every node can reach every other node And by definition, a tree, we're going to say, is a subgraph with no cycles. All right, let me just say that again, but slower. Remember, blue slides, you got to memorize and understand what they mean. Spanning tree is a tree within a connected graph such that every node can path to every other node. So you can reach from a single node, every other node in the graph, and every node has that property. And a tree is a subgraph with no cycles. So whatever we pick here needs to be both a tree as well as have this property that you can reach every other node. So here, let's try to use an example. If I just highlighted these edges and said this was my spanning tree, is this actually a spanning tree for this graph on the bottom here? Yes or no? What's wrong with this if you are saying no? A lot of people are saying no in chat, but why? We're missing this connection here, right? We have to connect here, right? It doesn't connect all the nodes. So we have to add this one edge here. Before we had this, and now we have this. And only after we added the way to connect this last node, do we end up with a spanning tree, okay? What if we added an edge here? If we added one more edge here, would this be considered a spanning tree? Why or why not? Go ahead and take 10 seconds to yourself. Okay, we're getting a lot more nodes in chat. Right? And people are saying it's not a tree, right? A tree can't have any cycles by definition I put here. So in this case, we would have to remove one of these edges for it to be an actual tree. Okay. So it's really important. It's really, really important to notice that we can have multiple spanning trees, right? They can be rooted wherever we want because this is really a graph. And we don't want to have any loops, which actually makes an interesting observation. Observation for spanning trees, we have exactly b minus 1 edges. All right. For a spanning tree on a graph with v nodes, we have exactly b minus 1 edges. Now I'm just going to give you 10 seconds to think about this. What happens if we have more? What happens if we have less? Right? Actually, let's just start with less first. What happens if we have less edges? And then what happens if we have more edges? I'll give you 10 seconds starting now to think about this. All right, so if we have less edges, what actually happens? Like if we know that it has to be exactly b minus 1. If we have less, then we won't have a connected tree, right? A fully connected tree. In other words, it doesn't span, right? Spanning in this case means that you connect and can connect to every single node from any other node, right? So if, for example, there's 5 nodes in this graph and we have one of the edges missing, so we have 4 edges, then by definition, we don't actually have a way to reach some of the nodes, right? This node can't reach any of these nodes on the side, so we don't actually span the entire graph. If we have more edges, go ahead and type in chat. What do you think happens here, right? This is just a rehash of conceptually what we were talking about right before, right? It has a cycle. It must have a cycle, right? In other words, it's not a tree. So a tree will have a spanning tree will always have b minus 1 edges, right? So an example of when it has more than that. So here is a spanning tree. There's 1, 2, 3, 4 edges that we picked. There's 5 nodes, so that checks out. If we added one more edge in any way, then we would have 5 edges instead of 4. And now we have a cycle here, which means that it's not a tree. All right. Let me just go ahead and send you a copy, by the way, of this slides in case folks want to follow along. Can MSTs apply to directed graphs? They totally can, and we're not going to worry about them in this class. The algorithms we look at will only work on undirected graphs, and we're not going to focus in on kind of the more nuanced cases with directed graphs just for now. You know, just because there's not enough time in the world to cover every single algorithm under the sun, right? Good question. Now, a minimum spanning tree just takes us to the next level. We know that there are multiple spanning trees in this graph, and right now it's unweighted, but pretend like these had weights on each of the edges, right? Here's an example of a spanning tree, right? Here's another example of a spanning tree that I just changed some of the edges, and you can have different kinds of spanning trees. Each of these edges, pretend like they had weights for a second. A minimum spanning tree is a spanning tree within a graph that has the least total cost when you sum up all the edge weights. All right, we know that we can have multiple spanning trees. Some of them are going to be more expensive and some of them are going to be cheaper if we have a weighted graph. Right now, there's no weights on this graph, but we could totally add weights if we wanted to. And the minimum spanning tree is on a weighted connected graph that has the least total cost, right? So there is a maximum spanning tree. That is correct. And that is something that you could, for example, see on an interview or on a quiz question or something like that if you wanted to think about that. But we're going to focus on minimum because that application is more obvious, like, for example, the case with Comcast. All right, so that might have still been a little bit confusing. Let's just go ahead and dive into an example. List all the minimum spanning trees for this graph. Here's the definition that we have from before. And in fact, let me just emphasize, it's not that you touch every single node, but it's that you can reach every single node from every other node, right? So let me just emphasize that while you take about 30 seconds to try to answer this question, right? Try to find at least 2 minimum spanning trees such that every node can reach every other node. There we go. I actually like this formulation better than what I had before. So again, you have some time. Think about what it means to be a minimum spanning tree. See if you can find some now that we've come up with some examples, and try to find at least 2, right? All right, you got another 20 seconds. Again, just try your best here, right? You're learning this. A lot of you are learning this for the very first time. I don't expect you to be perfect, but this is trying to apply what we just reviewed as a definition and apply it to the example that we see here, right? So I'll give you another 10 seconds from now, and then we'll all hit enter all at once. All right, what do you think? Give me some examples of what we have here. If you're confused or if you're not sure, go ahead and punch in question mark. It's totally okay for you not to know, or if you are still trying to figure it out, it's totally fine. But we want you to be able to follow along when we explain it, and make sure that you ask questions if you're stuck on anything, right? Even if you're not complete, go ahead and punch in what you have. Nice. We're seeing a lot of different trees here. Cool. So let's go ahead and take a look at some examples here. We know for a fact that we're probably going to use AB, right? Like this seems really obvious because this is the cheapest edge we have in the graph. And if we want a minimum spanning tree, we probably want to use the cheapest edge, right? Give me a 3 in chat if you're with me so far that we use the edge AB. That's probably going to happen, right? So let's just go through an example. Well, if we use AB for that reason, we probably use CD for that same reason, where CD is the next cheapest node. And it looks like we would want to be able to connect AB and CD together anyways. So that seems nice. Another thing we want to connect is like AB with DC. And we have some options. We have, in this case, we have this thing, right? Here's an option that we could do to connect A and B to D and C. We have this option here. And we also have this option here, right? We have 3 options here. So let's just go ahead and label these better. Let's say that we have AD, we have BD, and we have AC as options that we want in order to connect these 2 nodes with these 2 nodes. Which one do you want to pick? I'll give you 5 seconds. How about this? Actually, better yet, which is the node that we don't want to pick? Give me the node that you don't want to pick of the 3 options we have here. Okay, we're getting a bunch of people typing in DA or AD, right? Because this is really expensive. We don't want to spend 11 when we could spend 8. Remember, we don't care if we want to get, if it takes us a long time to get from A to D, as long as we can do it, and as long as the edge costs total are cheap. So let's just arbitrarily pick, in this case, I'm going to pick BD here. So BD is picked. And we're going to go ahead and look at the rest of the graph. Now we have to connect F and E. So I'm just going to pick some edges here. And you notice all the costs here are all 11. So it literally does not matter which edges you picked as long as F and is connected to the rest of the graph, and E is connected to the rest of the graph. So I just put some edges here. Okay, so here's an example. AB, we picked CD next, and then BD, which makes sense. AF, in order to connect to F, we have to get a cost of 11 no matter what, right? And then EF, I guess, is what we wanted to do. Because again, it doesn't matter if we do EF or EB, because no matter what, it's going to cost us 11 to get here. And so the edge cost, since this doesn't affect the total edge cost, we can pick either one. Okay. Likewise, we could do AB, just like before, CD, BD, AF, and what I had originally, which was BE. Again, since the edge cost here is 11 and the edge cost here is 11, it really doesn't matter which edge we pick for E as long as it connects to the rest of the graph and that we minimize the amount of edge cost total. All right. There's actually quite a few more here, right? You can see there's so many variations because we can decide either between, for example, choosing this edge and maybe we choose here instead, right? So we go and connect BE as well as EF, or we could go back and look at the edges between BD and AC and change it to AC instead. This would still connect the graph together. And then we can still pick some edges here and do variations therefore. All right. Someone mentioned in chat that sorting by weight seems to be a major component. You are so absolutely correct. That is such a good observation. That is a great conclusion to reach. Sorting by weight, the edge weight will be super important in both of our algorithms, and you'll see that soon. All of these have the same total cost. Someone asked in chat, what is the cost for all of these? Go ahead and type in chat. Who can do the math offhand? Each of these should actually have a cost of 37. All of these should cost 37, right? The reason why these are tied for 37 is there are no cheaper minimum spanning trees. All of these are going to be 37 as the total edge cost, all right? Type in 37 in chat if you feel good about this, that all of these are valid MSTs because they connect all of the nodes together and that they all have the same edge cost. This is the cheapest way we can deal with it. All right. If we just add all the edges that we've highlighted here together, it will give us a sum of 37. And that's all we care about, right? We're Comcast right now. We're all about that cheapness. Okay. Now, to formalize what we've been talking about, let's talk more formally about the minimum spanning tree problem, right? As always, we think about the input and the output. The input in this case is a weighted undirected connected graph G, which has some vertices and some edges as a set. Now, notice that we care about undirected, just as I mentioned before, we're not going to look at the directed cases. We're just not going to cover that in this class. They exist. There are minimum spanning tree algorithms that can handle directed graphs, but for the sakes of this class, we're just going to focus in on the undirected cases. The output is going to be a tree which has V and E prime, where E prime is a subset of E that minimizes the edge weight sum. Now, this is just a fancy way of saying that we have a subgraph, so a graph within a graph, right? Trees are graphs, remember? And this tree will be a subgraph here that has all of the same nodes as our original graph. That's why V here is the same V. All right, this V that I have in this line is the same as this V here. And the reason why I have an E with a apostrophe is that this is read as E prime. Let me just write this down. I didn't cover this in other classes, but this is read as E prime. This is how you say that, right? And this is saying, okay, E prime is going to be a subset of E. So there's going to be some subset of all of my edges that I'm going to pick that minimize the edge weight sum. Now, if you looked at the previous example, that was exactly what we did, right? We didn't pick every single edge that we could choose, right? There are 1, 2, 3, 4, 5, 6, 7 edges, and we only picked 5 of them each time we picked a minimum spanning tree. And so likewise here in the formal definition, we only pick some subset that allows us to form a tree such that we minimize the total cost weight. What are the benefits that an MST has compared to regular graphs and trees? That can already pick the, okay. So the question is, what are the benefits of a minimum spanning tree, given that we can already pick minimum paths with Dijkstra's? Remember, we're optimizing 2 different types of things. With Dijkstra's, we're trying to say, going from point A to all of the other points on the graph try to minimize the cost there. Now, the cost of the total paths that you take, if you add them all up together, might not actually be as cheap as a minimum spanning tree. A minimum spanning tree gives us two things for free. It gives us the cheapest possible set of edges, and it also gives us the minimum set of edges necessary to span the entire graph. All right. If you are unsure what the difference between pathing and the pathing and the total cost, like just remember what we said about Comcast. Comcast doesn't care that it takes us longer to get from B to E, because it, if it chose BC, it would be cheaper to get from B to E as a path. It might actually just pick BD, even though that costs us more to get there, right? So if you're a little bit confused, ask me during break. We'll go over it in more examples. We'll reach the break pretty soon. Okay. So if you're still a little bit confused, feel free to bug me and ask me good questions. You're not bugging me. Ask me good questions then. All right. Or ask me any questions you have. I promise you, I will be happy to answer. Anyways, we have these inputs and outputs. Things you want to notice. Both T and G are graphs, right? This is the way we formally define graphs in formal mathematical definitions. And that T and G share the same B. In other words, T will contain all the nodes that G contains, right? Because that's a spanning tree. By definition, a minimum spanning tree has to span, which means it has all the same nodes, which is why these V's are the same. And that E and E prime are both sets of edges on some graph G. In other words, this is a fancy way of saying E is a bag of edges, right, of some graph. E prime is also a bag of edges of some graph, right? A thing you should note, though, is that E prime is a subset of E. What that means is that if E, for example, is this set of edges, if we had A, B, BD, BC, and CD, then E prime could be this subset. In other words, we just pick some smaller amount of edges from our original bag, right? We just took some of the edges, but not all of them, and that's what E prime is. Now, this is not a proper subset for those of you who are about to ask the question. Mathematically, this could actually, E and E prime could be the same in some cases. Not always, but sometimes. Okay. If you have any questions, now's a great time to ask. Otherwise, we're going to take a 5-minute break. We'll take a 5-minute break. We'll come back at 6:08. All right. So go ahead, stretch, get some water, go to the bathroom, whatever you need. We'll come back in 5 minutes. And if you have any questions, now's a great time to ask. I forget, have I already used this image in a previous slide? I feel like I haven't, but I'm not sure if anyone has seen this one before. On my slides, at least. Maybe you've seen it on your meme groups. Okay, thanks for letting me know. It looks like this is fresh. OC. Someone says it's impressive you even make memes. I don't make memes. This is 100% stolen from Zoom memes for quarantines. Can you give me more examples of the difference between Dijkstra's and MST? We will see one of the algorithms for finding a minimum spanning tree will look very similar to Dijkstra's, and there's going to be kind of a subtle difference. Once we walk through some examples, hopefully you'll get to see a little bit more how it's different, right? The problem we're trying to solve is fundamentally different. For Dijkstra's, we're trying to start at a certain node, and we're trying to compute the cheapest path from that node to every other node in the tree. For a minimum spanning tree, we're trying to find the least overall cost of just having a tree. So really, one focus is on having paths, and then the other focus is on having a tree. So Dijkstra's is the shortest single source, shortest path problem. In other words, find the shortest paths from a single node to all other nodes, right? Minimum spanning tree is written down here. Minimum spanning tree is all about finding a tree, a single tree that minimizes the overall costs of every edge we use. All right. So it's hard to explain with an example and kind of illustrate the differences such that you feel comfortable with it. What I'm going to do instead is just going to show you a bunch of MST examples. And then overall, like over time, you're going to get more intuition just by working with them, right? I know that's not a satisfying answer, but that's kind of the way we're going to approach it. So E would be equal to E prime when the graph is a line. Yes, it would also equal to E prime if the original graph was a tree. That is such a good question. I love it because it shows that you're already thinking ahead of when or how MSTs work on certain types of graphs. If you have other questions, feel free to ask. It doesn't have to be that advanced of a question. You can ask some basic questions. You can ask me to repeat stuff too. As always, I'm happy to help you understand this material wherever you are. The whole point of this class is to help you learn. And the whole point of me is to help you succeed. So feel free to ask any other questions you might have. All right, we got 1 more minute for break. For those of you who are just chilling out in chat right now, what's something fun you did over break? Did you get to do something that you liked? Did you get to catch up on work? Did you get to binge some new TV shows? Watch some new anime? Maybe go out on some hikes or some road trips? A lot of people had a lot of cool stuff that they did over the week, or if they just stayed at home, that's cool too. I did a lot of staying at home and just chilling. Hiking, catching up on work, painted my room, nice. Worked on some midterm projects for other classes. I'm sorry you had to deal with that. Kayaking, nice. I watched some anime. Which anime did you watch? I'm currently keeping track of Jujutsu Kaisen and Wonder Egg Priority, which is like, both of them are crazy in different ways. Job interviews, makes sense. It all went to the Rust beta and trying to flip PS5s and GPUs. Okay. Someone had a car accident. I'm sorry. I hope your car is okay, and more importantly, I hope you're okay. That sounds really tough. You had work? Makes sense. Spring break doesn't apply for those of us with day jobs. Nice. All right, so let's go back and think back onto prims. So now we're going to talk about actual programs, actual algorithms to solve this. Before, we just solved a bunch by hand, right? And we kind of just did it however we did it. Now we're going to try to take some of that intuition and formalize it so that it is an actual algorithm that we can use and program. All right, give me prims in chat if you're ready to start learning again. Let's make sure that we're all here. Nice. This is really, like, every time I ask you to type something silly in chat, this is just a way for you to get hyped, to make sure we're all on the same page and to signal that we're about to start, right? Hopefully you are okay with indulging me. It's just nice to know that people are listening in and ready to go. All right, so for a way to find a minimum spanning tree, let's just go ahead and just pick nodes to visit, all right? One thing that we want to do here is to notice that we have to reach every single node. So why don't we just start at a node, and every node we know will have at least one edge that we care about. When we have a minimum spanning tree, every single node needs to have a single edge, at least a single edge leading out of that node in order to create a valid MST, right? So what I meant is, like, when we look back at this definition here, I said that, okay, every node needs to have an edge, right? If we are missing an edge, let's say we didn't have an edge for this node on the corner here, then this tree isn't connected. We have to have an edge in order to connect this tree. We need to have at least one edge. Okay. So in this case, when we're looking at prims, it's taking advantage of the fact that we know that we have to visit at least one of the edges to a neighbor in order to create a valid MST. So why don't we do this? Every time we visit a new node, just pick the one with the least edge cost, and that will be the way we connect and kind of build up our tree. That'll probably work, right? This is an example of a greedy algorithm. I haven't explained what a greedy algorithm is. I'll explain it next lecture. But the idea right now is that we're just going to do something kind of dumb and do the obvious thing over and over again. And since we do that, it's going to end up actually working, and we're going to build a minimum standing tree. Someone in chat earlier said that we probably want to sort the edges by their weights. And that's exactly right. We're going to do something very similar here. We're going to use a priority queue. And so let's just go ahead and dive right into the demo. All right. So we have a tree here. Let me go ahead and reset here. And prims is all about starting at a certain node. All right. Prims is all about, let me just write this out so that you are all following along. Where is my annotate? Prims, big idea. Start at some node. For all the neighbors we could reach, pick the one with the least cost. All right. So we look at 2, let's say. We just randomly pick 2. In this case, 2 has 4 different neighbors we could reach, right? And we just pick the one that's the least cost. In this case, we pick 0 because going from 2 to 0 costs us 12 here. All right. Give me a 12 in chat if you feel like you understand between all of these 4 edges why we picked this edge. All right. Give me a question mark if you need me to repeat anything. Again, I'm always happy to help you learn wherever you're at. So in this case, we have 4 different edges. We're trying to find the minimum standing tree, so we have to pick edges. And I'm saying that we pick this edge from 2 to 0 because that is the cheapest out of these 4 options that we have, right? And we'll do this over and over again. So if you're still a little bit confused, that's totally okay. We'll look at this and hopefully it'll start clicking a little bit more, right? For now, ignore the pseudocode. Just follow along as we go. So right now, our set of edges, because remember, a minimum standing tree is essentially defined by a set of edges, is going to start with 2, 0. Now we do that, we're going to go ahead and look at 0. 0 is going to have some edges that we care about as well, right? So 0 now has edges that we care about. It has this edge from 0 to 1. It also has this edge from 0 to 2. Now, of all of the edges that are highlighted in black here, in other words, the ones that are not orange and the ones that are not gray, which edge is going to be the next cheapest edge to visit that we haven't already visited? So which node will be the next cheapest to visit just based on the edge cost alone? I'll give you 5 seconds. We have options 1, 3, and 6, right? We already visited 2, so we don't consider this edge. But we have these 3 nodes that we could reach based on the way we've traversed so far. Go ahead and punch in chat. What do you think is the node that we want to visit here? Okay, a lot of people are typing in node 1 because the cost here from 0 to 1 is going to be 8. And that's cheaper than any of the other places we could visit, because we could visit 13. We could visit this edge, which would cost 13. We could visit this edge, which costs 14. We could visit this edge, which would cost 21. And all of that's not very good. So let's just go ahead and pick this edge here, right? Now we look at all of 1's neighbors. And based on that, what is the next edge we try to visit? What is the next node we try to visit? Right? People are saying 4 because that's cheap, right? Looking at all the edges, the cost here is 9. So we just go ahead and pick that. And then from there, we look at all of 4's neighbors. And now at this point, something interesting happens. We look at 4's neighbors. It has 9, but that released 1, so we don't look at that again. It has a way to get to 3. It has a way to get to 5, and these are the corresponding costs. I'll give you 10 seconds. We don't just pick the neighbors of 4. We pick the neighbors of anything we visited before, all of the things that are highlighted in black. What is the next node we visit, and what's the cost it's going to take? Go ahead and take 10 seconds to think about that for yourself based on what we have done so far. All right, go ahead, type in chat. Everyone is typing in that we're going to reach 3 and we're going to reach it through 14. One brave person said we're probably going to do this one instead, this 1, 2 edge. And they were right. You all got debated. All right, here's what happens. According to this code, at least this pseudocode down here, if we look, we always want to look at the next cheapest edge from a node that we can visit, right? So from 2, we could visit 1 again and have a cost of 13, and that's cheaper than anything else we had so far. So as a result, we're going to try to look from 2 to 1, but because it is already something that we visited, we already visited 1 before, we don't use that edge, we throw it away. We look and try to pick 13, but we don't actually use it here. All right. Give me a baited in chat if you understand how and why we looked at this edge, but then we discarded it. Because afterwards, then you're all right, right? We went from 2 to 3 and we picked 14, right? We picked 2 to 1 because that was the next cheapest edge from the set of edges that we could visit. Now, I trick you sometimes, right? That's the whole point of this class, because the more I trick you, the more I confuse you and then explain away your confusion, the more you get confused and then get unconfused, the better your brain's going to wrinkle, the more you're going to return and remember the information, and the more effective your learning will be, right? So I'm always doing these small, dumb tricks just so that you can actually remember this stuff a little bit better, all right? We discarded 2 to 1 because if you look, that would have created a cycle. All of you intuitively knew that we didn't want to do 2, 1 because we were going to create a cycle here. But in this case, the algorithm doesn't know any better. So it has to try to use the node, the edge from 2 to 1, realize that it's in a cycle, and then bail out. Right. So we'll see some code that does this more elegantly in a second. But for now, if we just continue, we'll look at 14, this edge from 2 to 3 that costs 14. Then we'll look at all of the neighbors of 3 in this case, right? And then of all of these nodes that we can visit now, because 3 is kind of a central hub, which node do we reach from here? Go ahead and type in chat if you have it. We should reach 5. A lot of people are typing in 6 or 7, but notice that this is cost 8. That's why there's a line here. This is an 8, not an infinity. So we go and we pick 8, and then we do this again. We look at all the neighbors of 5. We realize that going to 7 from 5 is pretty cheap. Then we go and try to go from 7 to 8, which is pretty cheap. And then we go from 7 to 6, and it's pretty cheap, right? At this point, we can actually stop. This simulation will have us go and try every single edge and look at all of the edges, but we're not going to do that. We're just going to go ahead and stop here. And my question for you is, once we visit 6, why can we just stop right away? Right? We're doing this differently than Visual Algo because I don't like the way Visual Algo has you learn this algorithm. We're going to look at some pseudocode instead. But once we visit 6, why can't we just stop right away? Go ahead and let me know in chat. What do you think? We visited all the nodes, right? So in other words, we have v-1 edges, or we visited every single node. So there's no need to have any more edges be considered because now we've already picked all of the edges that we will ever need to pick for our minimum spanning tree. This is why the v-1 thing matters so much, right? So in other words, we already visited all the nodes and have all the edges we need for our MST, right? Because we know that once we visit the last node that we hadn't visited before, then we have a way to connect all of the elements together already. You don't need to do anything else. So each edge is keeping track of its min cost to be connected to all other nodes. You'll see the algorithm in a second. We'll go ahead and take a look at some examples of the code now, right? So I'm going to go ahead and give you this pseudocode. This pseudocode is different from the Visual Algo code, and that's on purpose because, one, it should give you flashbacks. Some of you should already be like, oh, I've seen this before. Oh, no, oh, no, oh, no, right? Some of you will be like, oh, okay, I see where this is. Right. I'll give you 30 seconds to stare at this code. We'll go through it together. And what I want you to do in those 30 seconds is answer the following question. What does this code remind you of? Which algorithm kind of looks like this? All right, what do you think? What does this algorithm remind you of? Okay, we got some question marks, but a lot of people are spamming BFS as well as Dijkstra's. Now, it's really, really important. This is literally Dijkstra's, except there's one line of change. These two lines are the only thing that's different. Hopefully you see my screen here. Give me a yes in chat if you can see my screen, both sides, the left side and the right side. Okay, cool. So you can see here that this algorithm looks very similar to Dijkstra's that I have on the right here. You have this iteration where we look through all of the different nodes, and then we set the cost of a single node to 0, similar to what we do here. Then we make a priority queue using the cost or the distance array as the way we keep track of the different values inside of my priority queue and keep them sorted. Then while the priority queue is not empty, we're going to go ahead and look through every single node in the priority queue, right? So we have this delete min happening. And then for all of the different edges of the current node, we're going to see if the cost should be updated, because if we have an edge with a cheaper cost, then it should replace the current existing cost. And we update the priority queue based on the costs accordingly. Okay, you can see here that the only difference between the left-hand side and the right-hand side are how we compute the distance array. So here we call it cost, and it's literally just always going to be set to the cost of the current edge weight that we're looking at. W of v comma z means that we're looking at the edges and the cost of those edges. Whereas here from distance, hopefully you remember from the last homework, this is the path cost, right? So distance computes path cost from some source node S, right? Cost computes the minimum edge weight used to connect that node to the rest of the MST. All right. And this is, some people are asking, hey, what's the difference between MST and Dijkstra's? I'm not sure. This is one way to understand it. You can see the code on the left and the code on the right are very, very similar, but they're slightly different. All right. So I'm going to give you some time to think about this by working through an example. Let's just go ahead and look at the example we just had. And we're going to go ahead and do the same example now on a different node. Let's start at node 0 because that's what the pseudocode has us do. Okay. We're going to pause and do this one step at a time using the pseudocode on the left here. All right. I know that this can be a little bit confusing, so we're going to go through and work through it step by step. And we're going to try to do it fast, and we're probably not going to get through everything. But I'm going to do at least the first couple of steps, and then y'all can follow along and let me know if you're confused. All right. Let's start here. How many different infinities do I need to put in cost? Cost is going to be an array, similar to how we have the distance array for Dijkstra's. Go ahead and type in chat. How many infinities do I start with? Okay, there should be one for every single node in the graph. There are 9 nodes here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So there should be 9 infinities. And then the prev will be 9 nulls. All right. And what I've just done is I've done the first couple of lines of prims. All right. Give me a yes in chat if you're feeling good about where we are so far. If you're following along, give me a question mark if you're not sure what we're doing. Okay, so we're just trying to go ahead and walk through the algorithm step by step on this example graph, and we're starting with the first couple of lines, which initializes our cost and prev arrays. And at the beginning, there's 9 infinities for cost and 9 nulls for prev. Then we're just going to pick some initial node. In this case, we're going to pick 0, and we're going to set the cost of u to be equal to 0. So we'll just do that here. So at index 0 here, we'll set the cost to be 0. Cool. And then we'll just do this part, which says make a priority queue where we use the cost values as the keys. So in other words, we're going to try to look at all of the nodes and we put them in a priority queue and we pick the node that we haven't visited before that has the cheapest cost. In this case, node 0 has a cost of 0. So we look at that first. So V in this code, when we say V is equal to delete min, we're going to say that V is essentially equal to node 0. All right. Type in V in chat if you're still with me. Again, we made a priority queue. We didn't write this down. We're just remembering that the priority queue will look at the next cheapest node that we haven't visited yet. Very similar to how we picked it George, but not quite, because we're using the cost array. We're still using some array to dictate which node we look at next, right? So we're looking at node 1 first. So we look at all the neighbors of 1. Neighbors of 1, well, there's only 2 of them. There's 1 and 2, right? And we're looking for each of those neighbors. So for each edge from 0 to 1, right? And then the other edge from 0 to 2, we're going to check to see if the cost should be updated. Well, right now the cost to get to 1 is infinity. So we should probably update it from infinity to 8. Remember, this says 8. And the cost from 0 to 2 is 12, which is way better than what we had before, which is infinity. So those get updated. All right. So that's what happens right now. And that's what happens when we have V equal to our very first node, right? So the first V was node 0. And then we do this all over again, right? We update our priority queue so that we pick the next cheapest node that we haven't visited yet. I'll give you 10 seconds. If you are following along so far, which node do we have next? What is our second V? Go ahead and type in chat. Which node do we visit next based on what we have here? It should be node 1, right? Because of the things that we have in our priority queue, we'll only have these nodes. We already visited the node 0, so we don't look at it again. Someone asked, don't we update prev? Yes, we do. Oh, thank you. Nice, good catch. I always forget. So I need to remember in this case that both of these become 0. Prev in this case will actually just help us figure out what the minimum spanning tree looks like. So in this case, we have 0 and 0 here, which indicate that the edge that we care about goes from 0 to 1 and then 0 to 2, right? Because this is index 1 and index 2. Nice. Good call. I almost forgot. And you reminded me. So let's go ahead and look at 1 now. We're going to look at 1's neighbors. So 1 has 4 neighbors here, right? Not only do we look at 1, 2, 1, 3, and 1, 4, we also look at 1, 0. So what is going to be the 2 numbers we compare in order to look at 1, 0? Remember, this for loop, after we find the new V, we're going to look at every single neighbor, no matter what, every single edge, even if we visited it before. Very similar to how we did in Dijkstra's. So in this case, when we look at 1, 0, we're going to say that we don't actually update index 0 because the cost to get from 1 to 0 here, this edge will be 8, and that's more expensive than 0. So obviously we don't replace it, right? Because cost is only going to go down more and more and more. We do not update prev either, because again, we want to say that 0 was the node that we started with, so we're going to start that as null. All right. So that's what happens when we look at this edge here from 1 to 0. But do we update the edge from 1 to 2? Yes or no? My question is, now we're looking at this edge because this is our next neighbor we look at. Do we update this? Yes or no? Do we update cost here? Okay, people are typing in no in chat, which is correct. So that means, well, 13 was more expensive than what we had previously, which is 12. So let's not mess with that. Do we update 3? And if so, what do we update 3 with? Do we update node 3? Yes, we do. We update it with 25 because 25 is better than infinity. We go ahead and put a 1 here. And last, we look at 4 and we set that the cost here should be 9 and it comes from 1, right? Remember, when we visit our neighbors, we do it from the smallest labeled neighbor all the way up. So we looked at 4 next. Someone asked not 33. Oh, so someone is like, okay, wait, for Dijkstra's, we added the cost here plus the cost here. So 8 plus 25 should give us 33, right? That is true for Dijkstra's, but not true for here. Remember, prims and Dijkstra's compute different things. Prims only cares about the current edge we're looking at. Dijkstra's cares about the path? That's a really good point and really good question, right? Someone said not 33, implying that we want to go from here and add these two costs up. We only, in prims, we only care about the cost of the current edge, right? So we only care about the 25. We don't care about how we connected this all together before. Because again, trying to find the minimum spanning tree is different than trying to find the paths, okay? And I realize I'm going to have to harp on this a bunch going forward because this code looks so similar to Dystra's, right? Okay, so let's go ahead and keep going. We're going to do this one more time. Third V at this point, what's it going to be? If you are following along, you should know which node we look at next. Go ahead and punch in chat with your best guess. Right, in this case, we're going to have node of 4. Nice. So node of 4 will definitely be what's next. We're going to look at all of its neighbors, which again means that we'll look at 4, 1, realize that we don't need to update 1 because it's already really cheap. We look at 4, 3, and we realize that 20 is actually cheaper than 25, so we're going to update that. So we're going to update node 3 to have a 4 instead of a 1 because we want to go through this edge instead of this edge. And then 4, 5 is going to go from infinity to 19. All right. So I'm going to stop here because I don't want to go through every single V. It's going to take too long. But I want to make sure we feel good about this. So I'll ask you one more question. We updated all the neighbors here of 4. If you feel good about this, what's the next node we're visiting after this? I'll give you 10 seconds. Just make sure we're all on the same page here. Go ahead and punch in chat. What do you think? What's the next node that we're looking at? Okay. Most of you are typing in 2, which is correct, right? Because we're looking at the costs of all the nodes that we haven't visited yet. Right now, that cost, everything here, 6, 8, and 7, they're all cost infinity. So we pretty much ignore those. We have 2, 3, and 5. The cost to get to 2 is going to be 12. The cost to get to 3 will be 20. And the cost to get to 5 is 19. Well, that means 12 wins out, which means that 2 is what we want next to be added. All right. Okay, so we're going to stop here and just look now at the runtime, right? I know that some of you are still a little bit shaky on this. We'll have some chances to play around with this later. I would try your best to work through the simulation here. Ignore the pseudocode on the bottom here. Use the pseudocode from the slides. This is like the one thing I disagree with Visual Algo on how they handle minimum spanning trees. But we want to definitely keep track of how to update cost and prev for prims. So the final minimum standing tree will be a path made by all of the crown nodes. It doesn't necessarily have to be a path. Remember, we can have multiple edges coming from a single tree. Like, for example, we could have, if we had another node here, and it was only connected through, through 0, then this would not be a path, right? But it would be a tree. But yeah, we're going to use all of the node paths or all of the edges we decided based on prev to create our MST. Okay, I'm going to move on. So now let's try to figure out the runtime. All right. If you remember, or maybe you don't, but I'm pretty sure we covered this. The runtime for Dystra's is B plus E times log of V. Give me a yes if you at least vaguely remember this as a thing we said in class. Okay, yeah, you might not remember where this came from, but you should at least remember that the runtime for Dystra's is this. Okay, most people are feeling good. Okay, so if this is the case, what do you think happens here where the only difference between these two pieces of pseudocode is just this small change here? Will prims have the same runtime as Dystra's? What do y'all think? I'll give you 20 seconds to think about it. You can stare at the code on the left, which is prims. That's what we're focusing on this lecture. And you can stare at the code on the right, which is Dijkstra's, which is something we covered before spring break. We know that the runtime for Dijkstra's is going to be this mess over here, which is v plus e multiplied by log of v. What do y'all think? Let's go ahead and type in chat. Same or different? Okay, some people are saying, I don't know. Most people are saying same. And then a few people are saying different. That's what I'm seeing right now. All right. So let's go through it line by line. I'll try to explain what this code does and why it works and kind of like the runtime of it. And then we'll try to figure out how the runtime should compare. All right. So let's just ignore the right-hand side for now. We'll just move away from Dijkstra's and try to figure this out on its own. All right. So again, we're going to create a array of size v, 2 arrays of size v, and we're going to set all of the elements inside to be infinity and null, right? What's going to be the runtime for just this for loop here? I'll give you 10 seconds. What do you think the runtime for just this will be? All right, punch in chat if you have an answer. Okay. A lot of people are saying O of V, which is correct. So this bit here will be iterate through all V nodes, right? Inside of for loop is O of 1 work. Therefore, overall, for loop costs us O of V, right? If there are V nodes to go through, and each time we're doing constant amount of work, then constant times V is equal to O of V, right? So this will be O of V. This next bit down here should be O of 1, right? Because we're just literally picking a node and then setting the cost to be 0. So hopefully that seems like that makes sense. The next line is going to be the part that I think a lot of people get confused on when we're making the priority queue. Whenever we walk through examples, I don't do the priority queue part like very often, but we definitely should do it more. But in this case, let's go ahead and say, okay, this is going to take O of V times log of V. And I'll explain why, right? Because we have to make a heap of size V, right? Because a priority queue is basically a heap, a binary heap, like what we saw in heap sort way back when. And each call to heap add will take log of V, right? So if we have V elements that we're adding to a heap, and each element takes log of V time, log of n time, but n right now is the size of the heap, which is V, then we'll have V times log V be the runtime for this line. All right. Give me a yes if you're with me. If you feel like everything up until this line here feels good to you, or you feel like you're following so far. Okay, not bad. All right, great. Now, is heap add always just log V, or is it the worst case? It's actually just the worst case, because if you think about it, when you have the a heap at the beginning, it's empty, so it wouldn't take that long. And then as you add more elements in, then that's when it takes longer and longer, right? So this is actually kind of like an upper bound here. We're really using the big O notation to say in this case, like at most, it's going to take V times log V, but it's probably not going to take as long as this number of steps. Okay, so now we're going to say, okay, we want to check to see if H is empty. In other words, we're going to go through every single element in our heap, in our priority queue. So we're going to do the following V times, right? Because there's V elements in our heap. First, we're going to do delete min, which is going to cost us log of V. Because if you remember, removing from a priority queue is the same as removing from a heap. And that takes log of V time. Log of n, where n is equal to V in this case, right? So that means overall, if this takes log of V each time, overall, it's going to take V times log of V, right? So we call delete min V times because we do the following V times. So if each time it takes log of V, then it's V times log of V again, right? So far we have two costs, two factors of log of V. We just add those together. And then we look at all the neighbors, right? So if we think carefully about this, what the code is doing is it's looking at every single neighbor. Since the code here looks at every single neighbor, we're going to run the inner for loop e times, right? As many edges that exist in the graph is how many times we're going to run the inner for loop. The iterations in the inner for loop are going to run e times. Now, of all of these lines that we have here, where we check the cost, we set the prev, and we decrease key, which line is going to be the most expensive? 1, 2, 3, or 4? Which one do we actually care about here? I'll give you 10 seconds, right? This is inside of the for loop, so we're just trying to figure out the total cost of one iteration of the for loop. What do you think is going to be that cost? Or what do you think is going to cost us the most of all of these lines? Go ahead and type in chat if you have it. It's going to be 4, right? So this is decreased key is going to be expensive because we're updating the priority queue and we're resorting it. This is going to take log of v time. You just trust me on this. We talked about this when we looked at Dijkstra's, and I'm not going to rehash it. Just trust that this is going to take log of v each time, which means that overall it's going to take a total of e times log of v work, right? Because if we know that the for loop, if we count up all the times we use the for loop, it's going to take e times because we're going to look at every single neighbor. In other words, we're going to look at every single edge in the graph. And the decreased key takes log of v each time. Then we're going to have e times log of v overall, which means that if I do this in blue on the top here, overall for prims, the runtime should be O of v plus e, all of that in parentheses, multiplied by log of e. Log of v. The reason I got that, where I got that from is, okay, if we look at this first part here, we don't care about it because it only takes us O of v. That's not as expensive as all the parts that come after. So we kind of ignore this first part because that's not the part that's the most expensive, right? We use big O, which means we can ignore any term that's smaller than the terms that are the biggest terms in our runtime. Well, the biggest terms in our runtime come in 2 flavors. There's this part here, and then this part here. We have to add all of these up. So we have one factor of v times log of v, another factor of v times log of v. So we have 2v times log of v. In other words, we don't care about the 2 because big O. So we just have v times log of v plus e times log of v, right? We factor out the log of v on its own, and then we have v plus e. Hopefully this math doesn't seem too scary, but I'll just spell it all the way out. We have v times log of v plus v times log of v plus e times log of v. We know that these two can combine, and we don't care about the 2v times log of v because we're using big O, so we can ignore the leading constant, right? A 2 does not matter in big O land. And we have e times log of v, and then we just do some basic factoring, which means we can take these two, this should be a plus, and bring them out on their own and then multiply log of v afterwards, right? This is just like factoring in the distributive property. Okay. Give me a yes if you feel good about where we are right now. If this seems like it all connects, even if you're, you might still feel shaky. If you're feeling okay, just type okay. If you're confused, type in question mark. Seems like most people are feeling good. All right, here's the part that is a little bit tricky. So this is actually the runtime for Dijkstra's. It took me a while actually to figure out why this is going to be different, but here's the thing. The nodes of G are all connected, right? What I mean by that is that G will always be fully connected. You can get to every node from every other node, right? Since that's the case, then we can actually simplify the runtime. All right, here's how. We know that the number of edges in the worst case, will be equal to v minus 1 minimum. We also know that E will be equal to O of V squared in the maximum case. All right. What I mean is we don't know how many edges we have in our graph, but we know that this is a connected graph. Since this is a connected graph, then we must have at least V minus 1 edges, right? And we also know that in the worst case, there's going to be an edge for every single node pair in the graph, which means that we'll have, O of V squared edges maximum. If that's the case, then we can say that the most expensive part of this here is going to be the E. In other words, we can just say E times log of V, because we can say that either V will be just another factor of E in this case, or E is just going to be so big that the V doesn't matter, that we want to put this in terms of the number of edges. Yeah, it's weird that minimum is in all caps and maximum is in small caps. I'm not sure about the size of the priority queue. It must be E instead of V. No, remember, the priority queue is all of the nodes inside of the graph. We're adding all the nodes, so it has to be V, right? We'll have to, if you play around with this code, I hope you'll gain a better intuition, but you can always ask on Piazza or ask me after class. We have office hours after class on this stuff, right? So this is the leap of understanding that y'all have to feel like you understand. Basically, if the nodes of G are all connected, then the minimum number of edges we have is V minus 1, and the maximum number of edges we have is V squared. In other words, V is the part that matters the most. Between these two numbers, V is going to be the one that matters. E is going to be the one that matters the most. Sorry, let me try that again. E is the one that matters the most because you can put E in terms of V in such a way that E will always be bigger, right? Either E will be like V squared or roughly the same amount as V, which means if we put things in terms of E, that is an accurate statement. This uses O of N space. Yeah, in this case it would, because the Q would take O of N and these two arrays would take O of N. So 3N is still O of N. We don't really care about the space complexity all that much right now. But just to kind of harp on this one last time, let's just imagine we use this for a second, right? Let's just imagine we had a graph. One last time, imagine we had a graph where we have E is equal to V minus 1. In that case, this original derivation that we had is the same as saying O of E plus E, right? Because we can say that this is roughly V minus 1 and V, it's off by 1. So this is really saying E plus 1, and we don't care about the plus 1. So we have E plus E because big O times log of V, which is the same as saying O of 2E times log of V, right? I'm really hoping I'm not losing you all, but if you're confused, now's the time to ask. But like, let's also imagine where E is equal to V squared, in which case this really, like, we don't, if E is equal to V squared, then we don't really care about this, right? Because this is smaller than this value here. And we just want to put it in terms of the number of edges. And we would want that anyways. All right. Okay. I'm not sure if I lost people. I'm going to go ahead and take a 5-minute break now. We'll come back at 6:55. If you are feeling a little bit confused or feeling a little bit concerned about understanding this derivation, now's the time to ask. We'll just take 5 minutes to chill, go get some water, stretch your limbs, take some time to relax, and then we'll come back and talk about the last algorithm. Yeah, someone mentioned that if E is equal to V squared, then that's the same as saying That's the same as saying, let's see if I can get the parentheses right. V plus V squared, which if we care about big O, we can reduce down to just V squared, which brings us back to O of E times log of V. I apologize for all the parentheses. I don't have a good way of writing this so that it looks a little bit cleaner on text. But that is correct. That is a really good understanding, and I'm glad that you're thinking about it actively. Someone asked, hey, is it using O of N space or is it O of V plus E? So this is actually, the space being used should actually be O of V, right? When I said O of N earlier, I meant that N is equal to V, which is the number of nodes in the graph. Because if you think about it, we don't actually keep track of all of the edges and we don't store them. We only keep track of the number of nodes, which is kind of nice, right? If you understood everything up until this part, you're in really good shape, and you're gonna have to work a little bit to understand this. Going from here onward is the difference between like a B and an A, I think. Understanding the properties of graphs and understanding big O at the same time so that you can make this derivation, I think is one of the more tricky, challenging parts of the class. So if you don't get it right away, that's totally okay. It's something that you might have to study and practice and ask questions about. We have office hours after this, so you can ask as well. How are we feeling about this lecture? First lecture back. Is it how from a scale of 1 to 7, how are we feeling in terms of like 7, I understand everything, 1, I have no idea what's going on? Go ahead and type in chat if you're here and you want to vote. I'm not going to force you to answer, but I'm just curious if people feel good about this right now, and where you're at. Okay, we're getting some 5s, which is pretty good. Runtime's a little bit confusing. It always is. Totally understandable. If you understand the big ideas of what an MST is, what the algorithms are doing, and most of the pseudocode, then I would say you're doing well, because it's hard to take everything you learned in lecture and just understand it right away. That's why we have these videos, so you can watch them over again. My brain is still in vacation mode. That's fair. I actually picked MSTs to be the first thing we learn, because out of all of the things that we're going to have to learn, this is actually the most gentle thing. This is the thing that sucks the least. Once you go into dynamic programming, algorithm design, search problems, P and NP, approximation algorithms, kind of ramps up, right? I tried my best to be gentle to start us off easy coming back from spring breaks. If some of you are feeling closer to like 1 to 3 out of this 7-point scale, it's totally okay. Please come to office hours. Please ask me questions. We're going to do homework on this. So it is something that I expect you to think about, and we will have a quiz on this, right? So it is something that I need you all to be thinking about. But I'm glad that y'all are feeling good so far. I need a dose of Nico to calm down. My cat is currently taking a nap. I'm not going to bother him. He's doing all right, though. Maybe he'll want to play later on. I've taken the habit of feeding him before lecture, which helps a lot with ambient noise. All right. So this was Prims. Prims is all about finding the nodes that we start with and just adding on other nodes that we visit. Very similar to Dijkstra's, very similar to BSTs. We kind of just go through and we greedily pick the next cheapest neighbor that we can visit based on the neighbors we visited so far. Someone in chat asked, how is my dad? As most of you know, my dad was in the hospital to do heart surgery. He's out of the hospital and he's resting at home in Florida. I'm actually really, really happy about this. It's a big relief, and I'm really happy. Thank you all for your kind wishes, by the way. I know everyone has been super understanding, and know that like I really appreciate the support, basically. So my dad's doing as well as he can be, being someone who's a little bit older and just had open heart surgery. So he's healing up okay. He's at home. He feels very, very tired, but obviously that's how you feel coming out of major surgery. Am I teaching next semester? I am not currently teaching next semester. There's no plans. Next semester will be a Facebook engineer teaching software engineering, which I think is like 4310 or something, 4350. I don't remember the exact course name. But yeah. Okay, 4350. Am I teaching in the summer? I am not currently teaching in the summer either. It'll be probably your normal professor, whoever that is, whether that's a grad student or a faculty member. How about fall? No. This will probably be my last semester at GSU. Facebook is set up so that an engineer teaches at most 2 semesters at a university. And next semester, or next fall, will be a last engineer teaching software engineering. All right, so we're coming back from break here. This is a really, really cool graffiti art that I took a picture of in San Francisco. There's a guy who runs around and just paints, spray paints koi fish on the sidewalks, and it's really, really cool to see them. Hopefully you like koi as well. People are asking if they can connect with me on LinkedIn. You definitely can. Feel free to. I'll post my LinkedIn at the end of the semester and you can join there. And you can do it earlier if you want as well. I don't mind. All right, let's look at our last algorithm. We have about 20 minutes. So we're going to go and focus in on this algorithm called Kruskal's. Kruskal's is not as involved as Prim's. Let's go ahead and see how it works. Let's go ahead and type in K in chat if you're ready to learn about Kruskal's, so that we are all on the same page. We're ready to go. Nice. Thank you. Thank you. Okay, so Kruskal's is very different because before, remember if you looked at our example at the very beginning, our minimum spanning tree example where we just kind of picked the most cheap edges, like these we knew were going to be really good, right? The edge between A and B, the edge between C and D. These were edges that we knew were cheap and we knew instinctively that we wanted to pick them, right? So Kruskal's takes advantage of that instinct and does something very similar. In other words, Kruskal's is all about picking edges over and over again. Just pick the one that's the cheapest, pick the one that's the next cheapest, pick the one that's the cheapest after that, right? Now, there's a problem if we do this, right? What are the problems with doing just this, right? Instinctively, we know this is what we want to do, but there's some inherent issues with this. I'll give you 10 seconds to think about it, and then we'll look at it together. Is my screen still meant to be split? I can switch back. Actually, I should. So I'll do that now. There we go. Thank you for pointing it out. All right, go ahead and type in chat. What do y'all think? All right, we got some question marks. We got some votes that it's probably maybe disconnected, and we got some votes that interesting. Okay. So issue 1 may be disconnected, right? When do we stop picking edges? What if we picked too few, right? Issue 2, what if we create a cycle? All right. So the 2 issues we have to do in order to that we have to solve in order to invent Kruskal's from scratch is these 2. 1, we might be in a situation where the nodes, we just pick random edges and they don't form a tree, right? So we need to think about when we need to keep picking edges and when we need to stop. And then the second issue is, what if we create a cycle? If we pick the next cheapest edge and it creates some sort of cycle, that would be a problem as well, right? Turns out we can actually solve this relatively straightforwardly. Every time we pick a node, we want to avoid picking a cycle. So if it turns out that we're going to create a cycle, we just don't pick it and we pick the next smallest node instead. All right. Eventually, we will have picked enough nodes to make a minimum spanning tree, right? So we know exactly how many edges we need to pick. We need to pick b minus 1 edges. So we can solve issue 1 by picking b minus 1 edges. We can solve issue 2 by just not picking a node if it happens to create a cycle, right? That's all there is to Kruskal's. This is another example of a greedy algorithm which is, again, just a way of just doing the obvious thing over and over again. In this case, picking the next cheapest edge. Greedy means that we're like trying to minimize costs at each step of the algorithm. So in this case, we're trying to pick the least cost edge as much as we can, right? So Kruskal's is the following. Pick the next cheapest edge that doesn't create a cycle. Do this until we have v minus 1 edges. That's literally all Kruskal's is, which is why we can cover this in 15 minutes. So let's go ahead and take a look at an example of the algorithm. So we'll do it on this graph here. Now, I need to refresh because it still has source marked. That's a weird bug. Nope, still not the right tree. Not the right graph, I mean. This one? This one. Okay, there we go. Okay, so we're going to run Kruskal's, and Kruskal's literally just picks edges. I'm going to let this run, and then I'll explain it afterwards. You can see here that we're picking nodes. We're picking nodes that are super cheap. We picked this node here because it has a cost of 8. We pick this next node here because it also has a cost of 8. Oops, that's the end. So these two nodes both have, these two edges both have a cost of 8. Now between 0, 1 and 3, 5, how did we know to pick 0, 1 first? I'll give you 10 seconds. So we know that first we pick 0, 1, then we pick 3, 5. How did we decide the ordering of these two nodes, or these two edges? I'll give you 5 seconds to think about it. What do y'all think? Go ahead and type in chat if you know. If you have some intuition or if you want to give a guess. So someone said smallest weight, but if you look, they both have the same weight. They both have a weight of 8. Right? So we did pick the smallest, the cheapest edge, but we tie break by the smallest labels first. Right? So in this case, 0 is smaller than 3. So we pick that first. All right. So that's how, even though they had the same cost, we pick 0, 1 over 3, 5. Right. If we follow the same pattern, what was the next edge that we decided on? Go ahead and type in chat. What's the next edge we have? What is the next edge after 0, 1 and after 3, 5? If we're just following this rule of picking the next cheapest edge that doesn't create a cycle. Nice. So a lot of people are typing in 1, 4, which is true because that has a cost of 9. Now, after we pick 1, 4, we pick the other edge that has a cost of 9, which is 7, 9, right? Again, smallest label node beats out the other node, right? So 7, 9 goes next. And then from there, what goes next? Okay, people are typing in 5, 7, right? Because that has a cost of 11. So that happens next. And then some people typed in 6, 8, which is the next thing that costs 11. And 5, 7 beat out 6, 8 here. And then we just keep going, right? So we try to do 0, 2, that works out. And then we try to do 3, 6, right? So this is really important. At this point, we've been picking nodes and edges that have been just the next cheapest thing, and it's been working out for us. So we picked 0, 2, which has a cost of 12. The next thing we do, though, is to pick 3, 6. At this point, do we have a cycle? Yes or no? Yeah, we have a cycle here. This part here connects together so that we have a cycle. We can go from 3 all the way around to 3 again. So we don't want that. So we can't pick 3, 6. What's the next node we visit? Or sorry, what's the next edge we pick? Go ahead and think about that and type it into chat if you have it. What's the next edge? Okay, people are typing in 3, 7, which is correct because remember, that's the next cheapest node. What's important is that we always try the next cheapest node no matter what. It doesn't matter if it'll create a cycle because we don't know that it'll create a cycle. We only know after we go and check in the code, does it create a cycle? Which means that we have to check the node. We have to check it and try to pick it in order to decide whether or not it'll create a cycle. In this case, it will, so we don't pick that one either. What's the one after that? What's the next node that we pick? If y'all are following along now, you should know that we're picking 1, 2, because that's the next cheapest node. And again, 1, 2 creates a cycle, so we don't pick that. And only after that do we pick 2, 4, and we're effectively done. Sorry, not 2, 4, 2, 3. 2, 3 is the next cheapest node, and now we have all of the nodes highlighted. We've basically picked b-1 edges, and we can stop, right? Which is slightly different from what this code does. Okay, so if you feel good about that, right, we can do maybe one more quick example. Just real quick here, I'll walk through this example. No, I don't like this graph. Let's do the pentagram. Here we go. So this one's a little bit interesting that we'll look first at the least cost edge with the lowest label. In this case, all the things around it are 13. So we're going to pick 0, 2 first, right? Because the least labeled edge is 0, 2. Everything that has 13 of all of them, 0, 2 has the smallest labels. From there, we'll pick 0, 3, and then we'll pick 1, 3, and then we'll pick 1, 4, and then we're just done, right? So that one wasn't too interesting. Is there another one that we can do that might be more interesting? That was the tessellation. Okay, I'll leave it as an exercise later that we'll play around with. But as long as you understand the intuition here, literally this stuff here, if you write this down and memorize it, then you know Kruscals. Pick the next cheapest cycle that doesn't create a, pick the next cheapest edge that doesn't create a cycle. Do this until we have b-1 edges. That's it. Okay, let's do the runtime real quick. Now, a lot of people intuitively know to pick the smallest, but in the code, what we'll have to do is actually sort the edges by increasing weight, right? Someone, again, I'm very, very happy that someone mentioned this, that we probably have to sort it because that's literally what we do for Kruscals. We sort the edges by increasing weight. And then we're going to create a T here, which is just our set of edges. And we're going to go through all of the edges, possibly all of the edges. And for each one, we're going to see if we can use it or if it creates a cycle. If we use it, then we can go ahead and add it to our T. Otherwise, we just skip it and move on. As soon as there are no more edges that won't create a cycle, we're done. Yeah, as soon as we have b-1 edges, we can stop right away. So let's go ahead and find the runtime. So let's just think about the very first line. First line is sorting. We know we have to sort, right? How long does it take to sort anything? What's the runtime, let's say, of merge sort? Let's use merge sort, let's say. What's the runtime? If I have to sort a list of edges, what do you think the runtime for that would be? Go ahead and type in chat if you remember. What's the runtime of merge sort? Y'all are scaring me. What are you doing? The runtime for merge sort is in log n. This is one of those things you have to memorize. Even if you don't remember why, just memorize that this is n log n. A lot of people typed in O of n, and previous sections typed in log of n, which really worried me. Someone asked, can't we use radix? Sort of, you kind of can't because of the fact that edges, we're sorting by the weights. So these are like objects. So we could use radix if we thought really carefully. Actually, I don't know if we can, but by default, usually we'll use a comparison-based sort like merge sort, which will take n log n. All right. So this is going to take n log n. Since we know that we're sorting the number of edges, it's actually going to be e log e, right? Because the number of edges we have is e. So it'll be e times log of e here. And that's the first line. Now the for loop will run at most e times, right? Because we're going to go through the entire edge list. If there's e edges, we can stop earlier probably, but in the worst case, we'll have to look through all e edges. And let's just, assuming adding the edge to the edge list is cheap, and assuming that checking cycles is cheap, then overall we'll have O of E for the for loop. All right. So I have not explained how we're going to check cycles. That is something that we're going to look at maybe in a homework soon. But overall, between 1 and 2, which one is more expensive? 1 or 2? Go ahead and type in chat. Yeah, it's 1, right? 1 is definitely more expensive. So this is the one that we care the most about, right? So in overall, Kruskal's is dominated by the sorting factor, which means that we end up with O of E log of E. Now we're going to do a little bit of weird math again, right? We're going to say here that the number of edges at most is going to be equal to V squared, right? In the worst case, for a fully connected graph, where every single edge that could possibly exist exists, right? So it'll be O of V squared. I'm not going to do the exact calculation, but we know it's roughly the number of edges times 2. The number of edges squared. Right. So this is the original runtime. We're going to do a little bit of math here to do some and a little bit of observation to change the runtime here. Okay, if this is the case, then we can say O of E times log of E is the same as O of E times log of V squared. Give me a yes in chat if you're with me so far. Okay. From here, we're going to use this little known trick of logs where if you have an exponent in a log, you can bring it out as a constant coefficient of the log. So this line is just some dumb math trick that you have to memorize. And then lastly, since we don't care about the times 2 in big O, we can just say this. All right. So this thing is the same as this thing up here. Because of the fact that this is a fully connected graph, we know that in the worst case, the number of edges is going to be the number of nodes squared. And since that's the case, we can do some math and rearrange the runtime to be like this. All right. Which is, exactly the same runtime we had for Kruskal's for those of you following along. All right. So in fact, we're actually going to go ahead and do a comparison now between Kruskal's and prims in the time that we have left. We'll do that really, really quick. The runtime is roughly the same. Someone asked, when would you use one over the other? I'm not going to talk about that right now. We will think about that more carefully maybe later on. In the short term, what I want you to think about is the differences between prims and Kruskal's, and this is super important, right? So I'm just going to talk through it. Make sure you take notes here, because taking notes will help you remember it the most. So for prims, it looks like Dijkstra's, right? It looks like Dijkstra's. Explores nodes based on edges that we can reach. It has a source, i.e. a node we start at, and MST so far is always connected, right? If you remember, when we looked at the MST for this graph, for when using prims, we would go and add one node that is always connected to the previous nodes over and over and over again, right? But if we look at Kruskal's, we know that there aren't no past algorithms that look like this, right? If we look at Kruskal's, this looks different. Kruskal's is built different, right? We just pick some random nodes random edges that are cheap, and we just keep doing that as much as we can. Explore edges instead of nodes. No start node. And MST can be disconnected and slowly become connected as the algorithm runs. Right? So that's the main difference. When we look at Kruskal's, you can see here, Kruskal's doesn't care about connecting edges together. It literally just picks random edges that happen to be cheap And as long as they don't create a cycle, we add them to our MST. And anytime they do create a cycle, we just ignore them. Explore nodes based on edges that we can reach. Thank you for calling that out in chat. All right. So those are the comparisons that I want you to know about. You should definitely write this down. Let's go ahead and do takeaways now. Minimum standing trees are subgraphs that are connected, that are in a connected weighted graph that minimize the sum of the edge weights. There might be multiple valid MSTs for a given graph, and you can find the minimum standing tree that is for a graph that's weighted, connected, and undirected, either using prims or Kruskal's. Prims picks the next unvisited node with the cheapest cost, and Kruskal's picks the next edge with the cheapest cost that won't create a cycle, right? We have a quiz on this week. It's not going to be scary, but it'll be Dijkstra's, MSTs, prims, and Kruskal's. So you want to get those definitions clear in your head before the exam, or the quiz rather. And that's all we have for today. If you have any other questions or concerns, feel free to ask. Otherwise, thank you so much for your time. I will catch you later. We are in office hours now. So if you have any questions, feel free to stick around and ask. Otherwise, I will catch you on Thursday.